Good morning, everybody. My name is Horia Petran. I'm speaking from Bucharest, Romania. And together with Kurt Emil, we will moderate a session, which is the fifth and the last session of this eceee summer study. We had last days 4 great sessions, but I'm confident that this will be even greater, at least it's smarter, because the topic is on combining smart building features with energy efficient building. We have a very fine lineup of speakers. We have Katarina Lupagat from Linnaeus University in Sweden, assistant professor at the university. She will speak about smart technology for partially off-grid efficient, energy efficient multi-family buildings in Sweden. Then we will have Alvaro Gomez from INEST, Coimbra, University of Coimbra in Portugal, speaking on how to provide the readiness and flexibility of grid interactive efficient buildings. Then we will have Stratos Keranidis from DomX Home IoT Technologies in Greece, co-founder and research and development director, presenting the IoT and digital user interfaces to support the energy efficiency directive delivery. And last but not least, we will have Jiao from Fraunhofer ICI in Germany. She's a data scientist in the Fraunhofer Institute for Systems and Innovation Research in Karlsruhe. She will present about social trend tracking for user engagement analysis for smart buildings. We have 3 pre-recorded presentations and 1 live. Each presentation will be 15 minutes long, and then we will have a 5 minutes question and answer. So I will invite all the attendees and also speakers to put the questions in Huva, in the question and answer section, and we will try to answer in the discussion in the 5 minutes after each presentation. And hopefully we will have 5 to 10 minutes for an overall discussion at the end. So that is the plan. We have a nice session. Kurt, if you want to add something.
No, I think you did it tremendously good again for the 5th time. So let's just go on.
Thank you. So the first presentation, it's about evaluation of smart energy solution in a multi-family apartment building in Småland, Sweden.
My name is Katarina Rupegard, and I'm from the Linnaeus University in Småland, Sweden. And I'm going to talk about evaluation of smart energy solutions in a multi-family apartment building in Småland, Sweden. Småland is located in the south of Sweden, and this is also where Linnaeus University is located. We have 2 campuses, one in Kalmar and one in Växjö, where I am located. Småland translates into small countries and is historically famous for having lots of small regions and also lots of small, hardworking businesses. Some of these businesses have come together in an association that is called Goda Hus, Good Houses, and it is about energy efficient and sustainable buildings in the southeast of Sweden. Currently, there are 50 member companies in this association, and the members are small and medium-sized businesses and also a few municipalities. One of the member companies is a municipal housing company, and they wanted to construct a few multi-family apartment buildings. And they constructed 3 multi-family apartment buildings, and they were moved into during spring of 2020. In these multi-family apartment buildings, they wanted to introduce some smart energy solutions. And the goal was to be partially off-grid, and this is due to maybe that we've had a few power blackouts due to storms in the recent years. So one goal was secure the electricity supply. They wanted to do this through introducing solar panels and produce electricity. They also had a few solar hybrid panels, and these were also used. The cooling of the panels, the hybrids, produce more electricity through cooling, and the heat from the cooling is used to the bedrock system, and that increases the efficiency of the total system. They also wanted to introduce storage through hydrogen, but since there are unclear rules about how to manage hydrogen, they were not allowed to introduce this. So they had to change into battery storage. And they want to use this to peak shaving, so they can store electricity and use it while they need the most, and also increase the self-consumption and to be partially off-grid. They also wanted to introduce rainwater collection from rooftops, and they wanted to use this to flushing the toilets. And the purpose was to save drinking water and also not to use too much drinking water from the municipal system. They also wanted to introduce digitalization solutions for the tenants, and the purpose of this was to make the tenants more aware of their consumption patterns and make them want to save energy. You can see on the picture here that you have the building A, B, and C, and you have 3 buildings where they have installed solar panels, 2 with solar panels and 1 with hybrids, and these were utility buildings next to the apartment buildings. They also have the battery storage in a separate building, and also behind they have the rainwater storage. So some results. Prior to construction, they simulated the electricity production from the solar panels. And as you can see, the total consumption from October until spring, March sometime, is higher than the production, since we can't produce electricity from the sun during winter time here in Sweden. So very low production during winter time, but during summertime, the total production of electricity from the solar panels is higher than the simulated total consumption in the buildings. And the simulated self-consumption is quite high, but we can also increase that a bit more. And through using battery storage, we can increase the simulated self-consumption. We have some measurements from the electricity production, and you can see in the simulated production, the measured electricity production is very low in October, November, December, January, February. But from March, April, it's increasing. There was one fire incident in one of the utility buildings mid-March, since there was a tenant that was smoking and the fire alarm went off. So they had to disconnect a third of the solar panels in that utility building. So the production is decreased by a third from mid-March. And the solar panels are still not reconnected, since there is a debate on who is authorized to plug in the cord again. So 2/3 of the solar panels are currently producing electricity. So this is why one reason why the measured electricity production is lower than the simulated production. So the simulated production and the measured electricity production, there is a difference, and we want to the total consumption of electricity. We want to increase the self consumption from the produce electricity, and this is done by help from the batteries that are installed. So we have here also the bought electricity from the grid, which is much, much higher than the produced electricity. So if we look at the electricity production and also the self-consumption, we could increase the self-consumption by using the batteries, since you see that the battery storage is quite low, and comparing the battery storage to the sold electricity, the battery stores much less than is being sold. And one goal is to consume as much electricity as possible, and because it's better to consume it yourself within the building than to sell it onto the grid. And the battery was supposed to help with the self-consumption, so that the produced electricity was stored into the battery and then later used in the buildings. But there is a system, energy management system, that is not prioritizing the self-consumption or storage into the batteries. So there are some settings in that management system that is missing. Some more results from this apartment building area. So the solar panels is producing electricity, but it's selling more onto the grid than is being self-consumed. And still 1/3 of the panels is still not working due to this fire incident. And 1/3 of the panels were hybrids that are being cooled, and the cooling media is used, the excess heat produced is used in the bedrock system. And this is being logged, but has not yet been evaluated. The hydrogen storage was denied since there were no clear rules about how to manage this. So there was a battery storage solution installed instead. And the battery storage was supposed to help with self-consumption during summertime, but it's over-dimensioned and it's mostly unused since the energy management system is not prioritizing the batteries. There was a rainwater collection solution. They installed rainwater collection on 3 rooftops, and the rainwater is collected, and this has saved approximately 75% of the drinking water used for toilet flushing. But there was a faulty installation of a tap, and this was moved, and when they moved this, all of the log data was lost. So we had to start again with the data collection. The digitalization solution for the tenants. There is an website solution, and there is a follow-up soon to be made, but there are no official so far. According to a janitor in the area, there is one tenant using this frequently, the solution. So all the other tenants are not so interested in this solution so far. So the results from the data collection is that the data collection from this area was not coordinated. There were several companies involved in this data collection, and there were multiple software used, and they sometimes show different results. So there is a need for energy coordination. So the takeaway message here is that an energy coordinator should preferably be involved from the start. And the energy coordinator should make sure that everything is properly installed and that all the logging is working. The data should also be collected in a single platform or software and not multiple. And there should be an evaluation of the collected data after 1 year of full data. And the most important is that the conclusions and recommendations from the evaluation should be made available to the other companies in Goda Hus in this association, since all of the companies are small and medium-sized companies, and they depend on having new solutions evaluated and the recommendations and conclusions made available so that they can use these new energy systems. Thank you for your attention.
Thank you, Katarina. It was a very interesting presentation, and I think you are touching upon a topic that need to be evaluated much further. But I also see that there's a lot of challenges. It's of course not for you because you made the research and you have made the reporting, but there's a lot of challenges for the construction companies and the homeowners and others to have this to work. Because I think you point out all the challenges that we have. And as I live in Copenhagen, I also know Småland. And I know that there's a lot of small buildings there's a lot of distance between buildings in Småland. And if we imagine that all those buildings should be connected to the grid still, we would still have all the grid costs to connect those buildings. But on the other hand, with this solution here, you will only use a minimum of the energy from the grid. So I assume that there are some kind of double costing here, which I would like you to evaluate a little bit on, because we have to invest in the battery system for the individual houses, and we need at the same time to have the grid connected to the buildings because we need the grid. So how can we solve that issue if we should move further on with those kind of buildings who are self-supplying on energy?
Thank you, Kurt, for your question. I think it's very interesting because we need the grid. I agree. And we also need the grid for the water supply, electricity and water and all these supplies. But in my region here, Småland, we've had these storms where there was a power blackout, and we have had up to 2 weeks without electricity in some areas. So this is one of the reasons that they want to introduce these off-grid solutions to, in case of emergencies or something happens, they are able to have electricity and also water supply. But we still need the grid. So this is, we have to do it both ways, I think. So we have to invest in both solutions.
And do you work together with the energy supplier on this, or?
Yes, the energy supplier is logging the batteries also, and also the water supplier is also involved in this. One thing that we didn't realize was that when we stopped using municipal water, we thought that was a plus, that it was not to use as much water, but still the company pointed out that they still have the cost of purifying the used water. So they still have to have the piping to the house for the wastewater. So this is not only on the plus side for them. So we still have some things to work out to see that there is a benefit of all the solutions that are introduced. Mhm.
Then you also mentioned that there was not produced the same amount of electricity as what was expected, and you also gave an explanation about why. But you said it was one reason. Can you elaborate a little bit on the other reasons?
I think we've had so many things that had happened during this project, so I'm not sure. I think we have to. The solar panels are not working. That's one reason, and also the energy management system is not properly tuned in, so it's not prioritizing correctly. That is one reason. And I'm not sure the other reasons, if there are any more. So I have to do some more research about that.
And then a final question. This network here of the companies, you mentioned that the knowledge should be shared. Isn't there any agreement that in such a network you should share knowledge between each other in order to secure that you are optimizing the buildings? We should learn from each other.
Yes, I just came from a board meeting with this association, and of course they're in this association to share, but there are some small companies with just one employer, and there are also some municipal companies, and they are not really how to say, they're not financially driven to share with each other. They have these politicians that decide and they want to do. But of course, it's a benefit to be able to share. And we do that through the university. We have student projects and we do research projects, but it's not really in a structured way. So we're getting there, but it's very hard with this region to transfer the information from one company to another in a structured way. So, but we're working on that.
Yeah, we have a couple of questions from Alvaro, but I would like for the interactivity to ask Alvaro to unmute and to turn on the camera just to ask the questions.
Okay, thank you. Thank you, Katrina, for your presentation. It was very interesting. I was wondering about the energy management system. Does the energy management system has capability to manage some controllable demand or not? It only manages the supply side. Let's call it.
Yes, the supply side. I'm not sure because this is the second year we're trying to evaluate, and all the information is very, very well hidden.
Okay.
So I think the energy management system, it was supposed to connect together with the digital solution, so you can for the tenants. So the supply should be managed and stored into the batteries, but also in some way connected to the digital solution to be able to see when it's preferable to use the electricity and so on.
Okay, but when you talk about digitalization for tenants, that means that the interaction with tenants, it's required very often, or it is something that can happen when the tenants want, but the energy management system is an autonomous system. It makes decisions according to the tenant's preferences and desires and needs and so on.
Mm-hmm.
How the system works. Because this interaction, this responsiveness, it's an interesting topic, first of all, and it is, I would say, a major requirement if you want to go renewable.
Mm-hmm. Yeah, I think that the energy management system needs to be tuned in and set according to the to the settings that we choose. But I think the purpose was to try to get the tenants involved in this, to see how the energy management system could be tuned into their preferences. But they have not been so far very interested, maybe due to Corona, that we haven't been able to visit them and to knock on the doors and ask what they think.
Okay, thank you. Just one last question. When you talk about energy coordinator, what that means exactly? Do you think about a management at the higher level, higher aggregation management? Are you talking about this, or just a better individual management?
Actually, we have a university course developed from Linnaeus University, from my side, together with this association, Goda Hus, where we have both professors and also people from the industry from Goda Hus coming together and teaching about energy coordination. So we have this university course in this, and this is supposed to be a person employed maybe at the municipality or at the local housing company that should have this pointed out responsibility to collect all the energy data.
Okay.
So.
Thank you very much.
Yes, and thank you both for the discussion, and thank you, Katarina, for this honest presentation. I think there are many lessons learned for the other companies. Let's jump to, again, Alvaro, for the presentation on the smart grid, smart building, smart grid interactions.
Good morning, everybody. My name is Albert Gomes, and I'm here to present the results of using smart readiness indicator to access the readiness of building generated with power grid. Basically, this is about interaction between smart buildings and smart grids. And I will start with a very brief introduction, motivation for this study. Then I will say something about smart readiness indicators. What are the main characteristics, how can they be calculated, and so on. Then I will introduce the case study and main results of this case study. And in the end, I will go through the main conclusions. I think that we are all aware about the need to decarbonize our societies and to deploy a more sustainable way of living, starting with the energy sector, which is a major contributor to environmental impacts. Efficient use of resources, supplying our societies with energy based on renewable sources and electrification are pillars for the energy transformation we need to happen in order to decarbonize our societies. The point is that one of the key issues in this energy transition are challenges of this transition. For example, the characteristics of some renewable variable sources, namely variability and uncertainty, and the increasing demand that we are witnessing by the higher levels of energy efficiency, are challenges that requires higher levels of flexibility. That is, we need power systems to be more flexible in order to deal with these characteristics. And the importance of buildings has long been recognized, both because of the demand associated with them, which is a significant share, and also because of their potential contribution to flexibility. That is, it is not enough to look at the building and think about energy performance of the building. We can go beyond that, and it is necessary that the potential flexibility that exists in the building is made available to be used. And we need this flexibility, as I have said before, to facilitate the accommodation of higher levels of renewable sources and to deal with the increasing demand that we are witnessing. So taking this into consideration, you decide to introduce a new indicator. And basically this indicator tries to characterize the aptitude of buildings to actively adapt their functioning to the needs of the occupants, the energy networks, and also contribute to improvement of the energy performance. So basically, this indicator tries to characterize the responsiveness of buildings to different signals from the occupants or from the grid. The capabilities assessed are three: the readiness to adapt to the needs of the occupants, the readiness to facilitate the efficient operation of building, and the readiness to respond to signals that may come from the grid. These three capabilities. In order to calculate the indicator, a multi-criteria methodology was proposed to evaluate service in the building. Look, we have these three capabilities that are assessed. In order to make this assessment, we have 7 criteria. These criteria that are in colors in the slide. We have energy savings, flexibility, comfort, convenience, well-being, and health, maintenance, and information to occupants. And so basically the idea is that the total score of the building is a percentage of the maximum possible score. This way expressing how close or how far the building is from the maximum score. And basically the higher percentage is smarter the building, or the more flexible is the building is. The services covers 9 domains. These domains that are in this slide, heating, cooling, hot water, control, ventilation, and so on. For each service, we have a functionality level representing the higher functionality as smarter service. That is, for instance, we are talking about ventilation. If you think about ventilation, we may be talking about no control, about manual control, or about local automatic control associated with air quality sensors. So we have different functionality levels for controlled ventilation. And so higher functionality means a smarter service. Besides assessing besides calculating the SRI of the building, we try also to answer some questions. These questions here. The first one is, does a higher smart organization indicator means higher flexibility or not? Second one, to what extent can the SRI be used as a surrogate of an NZEB indicator, NZEB calculations? And what is the impact of the energy service provided in a building on the indicator value of the building? That is, if we have different buildings with different services provided, how the different services impact the SRI. The case study in this work, we used the protocol proposed by use. Here, the smart organization indicator value is obtained by the weighted sum of scores in each criterion. We used the weights proposed by consortium. You can see here, we have 3 different capabilities: energy savings, the response to the user needs, and the flexibility, and the weight. The weights are equal. And we have here the criteria, the impact criteria, and the weights are here. Okay. The building used was a building of the University of Coimbra. We have used the simplified assessment, and basically the tools provided by consortium have been adapted to the case study. Just a very rough idea, but general idea about the building. We have 3 different natural gas boilers with predefined temperature set pointings. There are heat pumps in the amphitheaters, and there is resistant heating in some places. There are some basically we are talking about professors' offices. There are no hot water. Regarding cooling, there are heat pumps in the amphitheaters. The control depends on demand, and there is no information, local or centralized, and it is operated according to a predefined schedule. Regarding mechanical ventilation, it exists only in amphitheaters. There is no information, also local or centralized. Sorry. Regarding the other service lighting, there are some places with present sensors to control the lighting systems in some places. The lighting in corridors is controlled either by clock or sensors. The envelope, there are some protecting devices like fixed overhangs. Electric vehicles, there is one charging point, but it's not possible to control the charging process. Monitoring and control, HVAC systems are functioning with the previously scheduled, previously defined. There are some movement sensors to control some lighting circuits. So just to have an idea about the different services in this building. And with this services in this building, the score for this building, it's really poor. It's only 12%, as you can see. If you take a look on the three different capabilities, we have 16.7% for savings, almost 40% for the user needs, and 6.5 for flexibility. So very, very poor performance regarding this indicator. And why is that? Because basically the control does not control of different services in different services does not exist, or it's manual control or local control, but without manual control. There is no information to the users, and there is no management capabilities. And so we have a very poor SRI score for this building. So taking this into considerations, we have assessed a few improvements. First, we have assessed individual the impacts of individual improvement in the SRI. And then we create a scenario in which we simulate all the previous improvements, and then last scenario in which we implement all these improvement measures plus demand-side management capabilities. So what improvements are we talking about? Talking about improvement communication with occupants, improved space heating control, improved storage strategies, and electric vehicle storage, and then the fifth scenario is implement all these improvements. The results of these are described in this table. This is the SRI value, the actual value, 12%. When improved the communication with occupants, we slightly improved the SRI value. And when we control, we use sensors to control some service like lighting, we also increase slightly the SRI value, storage. And so only in scenario in which we implement all the measures plus the management capabilities, we improve in a significant way the SRI value, 33.45%. But even so, if you think that this is a percentage, you can see that even when we implement all these measures plus the management capabilities, we get a not very significant smart organization indicator. Well, we're talking about absolute values. If you think about percentage or relative values, we have very, very interesting growth. But as you can see, 34%, it's not big SRI. So the point is, why is this such a small SRI? Because we implement improvements, communication, sensor, storage, and electric vehicles. But for instance, if you talk about storage, we implement the storage capabilities and the local management capabilities, but we not implement two-way power flow, for instance. The electric vehicles, for instance, we also implement increased number of storage of those charging points, but not implement also two-way communication, two-way power flow. So the coordinate demand side management activities of different technical buildings is also not simulated. And that's why the SRI is still poor, not very good. Well, we have here the actual situation, the implementation, the results of the whole measures, and the whole measures for demand side management. As you can see, the percentage in each one of the capability, it's not big. Despite improved, significantly improved, it's not as big as that. Conclusions. To have an SRI score, the building has to be responsive to request. That is, it has to be flexible. Do not forget we have 3 capabilities, and if we use the same weight for each one of the capabilities, of course, if you want to have a very high smart readiness indicator, you need to have a flexible building. A building getting a high smart readiness score, it is a very high energy performance building, but the opposite may not be fine. Okay, that is high performance energy building may have a worse SRI. Comparing different buildings with different services should be done very, very carefully. Basically, a building with fewer domains may get higher or lower score depending on the score of the same services. So basically, this is a really interesting, really important indicator. It has to be used very carefully, and mainly you should not forget that the methodological tool used to calculate this score, this indicator, is a multi-criteria methodology. We have weights. If the weight changes, the score changes. Different weights for sure produce different scores. So it is important. We need this flexibility to be made available. This potential flexibility that exists in buildings, we need to use to make them usable by our systems. But pay attention, because this indicator is an indicator, no more than that. Thank you very much. And now I'm ready to talk with you about these issues and to respond to your questions, of course. Thank you.
Thank you, Alvaras. It was also a very interesting presentation. I have 2 general questions for you. I think I will raise the first one first, and then I will take the second one afterwards. But if those smartness readiness indicators, they are divided into 3 areas: energy efficiency and user involvement, and then connection to the grids. I think it was with 1/3 each. Is that the right way of doing it, or would you, with your experience, suggest to set it up in a different way?
That is an hard question, of course. The point is we have 3 capabilities, and the weights, it's just because we want in the end to have a score, a value, right? And we made a weighted sum of all the scores, of all individual scores. When the weights are the same, basically you are saying that they have the same importance. The degree of importance of each one of them, it's the same, basically. Is this the correct way? It's one way to do that. We can simulate different weights, but this is one way to do that. And we should not forget also that, for instance, when you're talking about the capability of talking about flexibility, for example, and the capability of being responsive to the user needs, we should take into consideration that sometimes these may be conflicting objectives. And of course, we need to work on these conflicting objectives. And basically, my idea is that, okay, you should be responsive to the grid, take into consideration occupant preferences, needs, and desires. And if we take this into consideration, the weights in some way, it's just one way to operationalize the methodology, the implementation of methodology. just to finish my answer, I do not see these weights as degree of importance, but most as a way to operationalize the methodology.
Mm. And then the second question, but before that, also a comment. I would assume that you will agree that we should have a common European message for this, that we should all use the same method, because otherwise we would not be able to compare buildings in between each other. And that leads me to the last question here. Your SRE value was 12 for the building, and then you showed how to optimize it and get it to 33.5. What kind of benchmark do we have here? Is this is 33 good, or should we reach 100, or what should we do? What would the benchmark be to other buildings?
According to some experiments, the values or scores between 10 and 30 are common in first buildings. If you are asking me, is this good or bad? Well, I think if you want to, because the idea here is to make the potential flexibility that exists in buildings available to be used. We should not forget that smart grids, one of the main characteristics of smart grids is the integrative characteristic of demand. That is, the resource that is on demand side must be used in the operation of the grid. And if you want to make this flexibility available, we need to have flexible buildings. With 33% or 40%, I do not think we have flexible buildings. As you mentioned, we simulate some improvements, but even with these improvements, the SRI is still poor. But why? The point is that basically we try to simulate improvements that are not expensive and that we think that are feasible, but we can do much more about that. For instance, when I'm talking about electric vehicles or charging, we can implement, and I think that, there are people working on this, in two-way communication, and for example, to provide flexibility to the grid. And in this way, we can improve the SRI. So the point is 34%, it's a typical value, but it is not enough, I think. From my perspective, if you want to make the flexibility available, the potential flexibility that exists on buildings available to be used in a greener grid and sustainable grid, I think it's not enough. We need to improve. And basically,
thanks.
Sorry.
Yeah, thanks.
Thank you. I'm a bit cautious of the time, but still we have a short question from Katarina, and I will choose to read it. Was this an old building university for the case study, and was this in use during the pandemic?
It is not an old building. It is from the 90s, from last century, so it is not an old building. But the point is that I think the poor score is due to the control capabilities. We have manual control capabilities, local control, but basic. So talking in a SRI language, we have basic functionalities only. Is that? The second part of your question, sorry, it was about the pandemic.
Yes, I know it was a simulation in your presentation, but the question is in use during the pandemic, the building?
If the building is in use during the pandemic? Yeah. Yes. Well, yes. Nowadays we have already in-presence classes. Everything it's working in a new normal way. Let's call it. But we have already people. But during the worst months of pandemics, there was just a few people in building. Not basically we were all confined at home.
Okay, thank you very much. Thank you for the presentation and for the clarifications. And now it's time to go to a presentation from Stratos Kiranidis. It will be about IoT, Internet of Things, and digital user interface to support and to nudge, in fact, the Energy Efficiency Directive. Stratos, you have the floor.
Hello, good morning from me. Can you see my screen?
Yes, could you switch to presenter mode? Yep.
Now?
Yes, now is great. Go on.
So this is my name is Stratos Keranidis. I am the R&D director of the Domics Home IoT Technologies startup. We are located in Thessaloniki, Greece, and this is part of the work that is done in our Horizon 2020 project NUDGE. And this work has been prepared in collaboration with Philippos Anagностopoulos from the Institute for European Energy and Climate Policy. We will start our presentation by providing the background for the Energy Efficiency Directive Article 7 and see how it couples very well with the work done within Project NUDGE. So the Energy Efficiency Directive requires member states to achieve an annual reduction of 1.5% in national energy sales in two different ways. So the first is through the implementation of the energy efficiency obligation schemes, which oblige energy companies to carry out measures that can improve the energy efficiency for end consumers.
Would you please help me with the volume?
The other option is to perform alternative measures, which can be implemented as complementary measures to support the implementation of energy efficiency obligation schemes. So the amending directive that came up in 2018 increased the target for additional savings up to 0.8% of the annual final energy consumption for each member state. And there is a clear emphasis on the importance of monitoring and verification. So what are the energy efficiency obligation schemes? They are set as an obligation to energy distributors and energy suppliers or retailers, and they are pushing them to achieve energy savings, especially on end consumers. They can be implemented through a different way on each member state. So every state is flexible to specify the scope of the obligation, how the targets can be achieved, to set up their own methodology for monitoring the energy savings, and also the process for verifying and controlling the ability to achieve energy improvements. Typical measures result in implementations for building renovation, the development of energy efficiency services, energy audits, and public procurement rules. And on the small screenshot on the right-hand side, we can see the introduction of the energy efficiency obligation schemes in different countries, marking especially the starting date. So what can we consider as alternative measures? Alternative measures have also been widely deployed, and they can be grouped in different types of measures, including potentially the inclusion of taxes for energy and CO2 transactions, the provision of financial incentives to energy consumers, training and education campaigns, and alternative measures similar to these ones. There is also the ability to combine the energy efficiency obligation schemes with alternative measures, and this is what is done in most countries across EU. Focusing more on Greece, we can see what is the progress for the implementation of these measures. So during the first period between 2017 and 2020, the energy efficiency obligation schemes covered up to 10% of the Article 7 target. So in total, 29 parties were obliged to either implement measures trade with third parties, or use the buyout option. And for the upcoming period of 2020 till 2030, there is a national revision of the scheme that is currently ongoing with the Ministry of Energy and Environment. And we expect to see a radical differentiation and much broader implementation. So as part of the alternative measures, we expect to see also the energy upgrade of residential, public, and industrial buildings, the improvement of energy efficiency through energy service companies, and the introduction of energy managers in public buildings and other measures as well. For the rest slides, we will focus on how the NUTS project promotes the delivery of the Energy Efficiency Directive, and especially Article 7, through the combined use of home IoT and digital user interfaces. So just to set some background for Project NUTS, we know that there have been several studies in the past, already since the 1970s, where different monetary or even in-kind incentives were used to affect the consumption decisions. Recent studies have shown that we don't need to resort to financial provisions or these types of incentives, but we can revert back to more behavioral characteristics. And by far the most influential of these studies is the work prepared by Richard Thaler and Gus Sunstein in 2008, where they introduced the notion of nudging. So nudging has already been adopted, especially in behavioral interventions in the energy domain. But in NUTS project, we try to take a step further by combining the use of home IoT equipment for energy monitoring and management, the employment of digital user interfaces for engaging users into long-term use of the offered services, and finally, behavioral measures that will be combined on top of the digital infrastructure to promote long-term behavior change. So what is the consortium behind the NUTS project? We have 11 partners with different backgrounds and expertise. So for our R&D institutions, we have 2 policy experts, 1 energy supplier, 2 SMEs, 1 consumer association, 1 energy cooperative, and 1 education expert. What are the objectives of the project? We have 4 major objectives. The first is to tailor the design of the behavioral interventions to the different variables from the pilot populations that are engaged into the project. We will execute extensive field trials considering 5 different pilot populations. We will develop a systematic research protocol to measure the impact of the interventions and also evaluate the energy efficiency improvement behind our interventions. And finally, we will consolidate the findings that will come up through our pilots into recommendations to policymakers. Which are the 5 pilots? We have designed 5 totally heterogeneous pilots that are taking place into 5 different countries, which are Greece, Belgium, Germany, Portugal, and Croatia. We consider different environments, including residential buildings, schools, and energy communities. And we consider a wide range of different population parameters, like including young children, different income classes. We consider different energy carriers, namely electricity and natural gas. And we include also, let's say, more advanced cases like residential prosumers and TV drivers. So among the 5 pilots that are already ongoing, we will now focus on the first pilot, which is the one taking place in Greece, and which considers the efficient control of heating and domestic hot water preparation for natural gas boilers. So how do we implement this type of intervention? We introduce the heating controller of our company, Domix, at natural gas consumers. So we attach the device with a legacy boiler that has no previous smart functionality, and we improve the way that it operates. So the user can now control his heater both through the already existing thermostat and also through our smartphone application. And what are the benefits that come through the use of this technology? The user has detailed consumption monitoring. They have the ability to remotely control their heating, to set heating schedules, and to exploit the improved climate comfort and improved energy efficiency that can come through this technological improvement. On top of this infrastructure, we also plan and are already actually providing indicative nudges to end users. So what are these type of nudges that we consider? We prompt the users, for instance, to switch from manual control to automatic control. And what does this case cover? So the algorithm that is running on the edge, on the actual device, is able to detect the minimum comfort and economy trade-off that can be achieved from the specific building and the specific user requests. So instead of letting the user select the trade-off that he likes to apply, we let the algorithm do this and propose, let's say, the best trade-off between these two values for the specific user and building type. We also provide personalized feedback on the achieved efficiency improvement, so the users get detailed reports on how their system performs now through the new technological installation, and previously when the user used to control their heater just through the pre-installed thermostat. We also visualize the environmental consequences of non-efficient actions. So consider, for example, that when the user will consider a much higher target temperature, he will get a personalized feedback message on how this selection will affect his bill, the CO2 emissions, and the energy costs. And finally, we plan to compare the performance of similar households that are located within the same neighborhood or city. And through this social type of nudging, we like to push users to perform better than their other members of their group. On this slide, we focus a bit more on how our energy efficiency improvement comes from. So we will show how the same home in Thessaloniki is heated between two different 24-hour periods in December 2020. So these two different days feature similar outdoor temperature conditions and also similar requests in terms of times of duration of activation and similar target temperature requests. So in the legacy mode, as we call it, we capture the way that the boiler used to operate before our weather adaptive heating algorithm is enabled. So in this scenario, the heater and the radiators use a fixed boiler temperature, which is set to 65 degrees. And the estimated consumption for this scenario accumulates to approximately 47 kilowatt hours for a whole heating day. When we employ the weather adaptive heating algorithm and we set a equal balance between comfort and economy, we reach the consumption of 34 kilowatt hours and achieve gas consumption reduction of 27%. Of course, you can understand that the amount of reduction depends a lot on the trade-off value. So even in the case where we have equal balance, we can achieve significant energy savings. Concluding our presentation, we can show here that there is a clear relevance between the targets of Article 7 and the work that we are currently working on in Project NUDGE. So the methodology of NUDGE project is able to improve the energy efficiency for different types of buildings, while we specifically focus on the case of residential households. We have developed a valid energy savings calculation methodology, which would be able to guarantee the request of the Article 7 for having a very robust energy savings calculation algorithm. We also promote long-term energy behavior change as we offer a combined approach between different technical measures and also behavioral interventions. And finally, we are more than welcome to consolidate the findings that will come up from our pilots to provide it as a recommendation to policymakers. And this is actually what we are trying to do, especially in the case of Greece. And specifically today, we have a workshop where we talk with the national regulation bodies and provide our intermediate pilot findings to them as a proof of concept. So the preliminary results that we have managed to collect suggest that the combination of home IoT technologies with digital user interfaces and also non-G interventions can help to meet the requirements set by Article 7. But of course, we need the support of energy providers that they will adopt this solution or relevant solutions and mass roll out this to interested consumers. So we are looking forward to see how efficiently relevant implementations can take place within different member states. So this concludes our presentation, and thank you for your time.
Yeah, and thank you, Stratos, for this nice presentation and also for sticking to the time. If anyone has some questions, please do ask.
I have one question. It's we had a presentation a few days ago regarding interfaces between different products in the buildings, where they have different setups. Have you any ideas about how we can connect the different products? Like you had the boiler in the gas boiler in your presentation, but what about the ventilation system, the mechanical ventilation system, the shadings, and so on? Have you any thoughts about how to combine that into your system?
Actually, this is a very important question that we also tackle or try to tackle in other projects as well. So the main problem here is that every company, whether being smaller or bigger, they try to, let's say, deliver their own ecosystem and try to lock their customers into their products. But the most important, let's say, ways to tackle this are to set up higher level ecosystems, especially developed like open source projects, where any, let's say, interested party can implement their own let's say, translator to a greater system. And this is what we actually do. We are developing our solutions as compatible with open source projects like OpenHub. And we exploit this in the bigger scenarios of, broader scenarios of energy management at home. So you can see an idea here on this small screenshot here. So we have, we incorporate other types of let's say, automation solutions that can be used under the same application. And we also offer connectors to match these functionalities with the open source project of OpenHub, as we mentioned.
Thanks.
You're welcome.
We have other 3 questions. Let's take them short. Katarina, would you ask the question, please?
Yes, I was just wondering, you said that you the project in Greece where you could let the households compare to other households in the neighborhood or other cities. Is this possible due to GDPR, the regulations to share, or how is that performed?
Yes. Thank you for the question. So, of course, GDPR is a big, let's say, barrier when you try to compare performance among peers. But we try to do this in an anonymous way. So we offer only specific information provided by end users. Let's say the square meters of their apartment or the approximate location. And well, actually, it's not the location, it's the climatic zone that they refer to. So we compare peers only in terms of these, let's say, subjective parameters. So you don't know which is exactly the peer that you are being compared to, but you know how well you perform and guess against other group members.
Okay, thank you.
Thank you too.
And also a short question from Xiao.
Yeah, Actually, I was very interested in this topic, and I would like to know which kind of uh, like survey data or what kind of data you already used for the nudging, so that we can expand your nudging to the person you use for experiment to the larger size.
So you refer to the ways that we collect survey data from end users?
Yeah, this is the first way, and I mean, like, so which kind of person you also already use for the experiments, so that so we want to if we want to use this nudging measurement to the to others, not only the experiment person, how we can do that. So yeah.
Yes, yes. So the methodology that we employ is quite open. We just focus on 5 different pilots, so it's quite generic. There is no clear focus on specific populations or pilot user types, let's say. We have also executed a large survey across Europe. We collected approximately 3,000 samples to understand what are the different types of consumers that are interested in such technologies. I don't recall the exact number of main user groups that we identified, but they are not. It's not a big list. It's less than 10, if I remember well. So we conclude that our approach is quite generic.
Okay, so like how many persons like for your is already in your experiment?
Every pilot has a population of 100 households, so approximately 2.4 participants per household. This sums up into a large population behind the pilots.
Okay, thanks.
Yeah, thank you, because this is getting really interesting, because we will detail this issue in the next presentation, which is by Jiao. It's about social trend tracking for user engagement analysis for smart buildings.
Good morning, everyone. My name is Jiao Zhao, a PhD student of Fraunhofer East and Utrecht University. Here, I'm glad to introduce our work, which combines spatial analysis with multiple data-driven approaches to analyze how the concept of smart buildings diffuses in Germany and in which topics users are highly engaged. As previous presentations have mentioned, smart buildings could address the challenges of global energy sustainability. Although the concept of smart buildings has been widely discussed, its services are still rare in practice, especially for residential buildings. How decision makers and end users can be nudged to participate in smart buildings is still a question. Normally, this kind of user adoption or user engagement analysis are based on services. This paper will introduce user-generated data into, so that with automatic data collection process, we can get at least millions of data within a narrowed concept like smart buildings without social desirability bias. So now you can just imagine you have 1 million services with 150 keywords representing over 30 years data. How you can analyze them and show a beautiful result. That is a reason why we import visual analysis into, so that we can easily to understand a fuzzy concept and efficiently represent the concept spreading over a long time period. To assist the public interest from different aspects, we select online news to represent the macro dimension and social media, especially for Twitter, to stand for the daily attitude of end users. The overall workflow is divided into 2 parts like this picture. So data collection and analysis. For data collection, to embed the intelligence of the academia and the industry, we first search the concept in patent database and extra keywords in the descriptions of the search results and their categories by automatic algorithms.
The top 20 extract keywords in patent database are regarded as the basic keyword list. With the basic keyword list, we start web scraping among all the scraped text, the extra keywords again with the automatic algorithms, and use those algorithms extracted keywords to scrape others until the top 300 keywords are fixed almost. So it's like iterative work. So there are the keyword extracts by Twitter, and this is from the online news. Although both of them are highly related to the smart home and photovoltaics topics, tweets tend to discuss more about smart products. Like here you can see Philips Hue, Amazon Echo, Google Home. While online news put forward more abstract concepts in the energy domain. In this way, smart building diffusion among Twitter is driven by enterprises in an active way. And when the involved companies have reached a certain amount, it will influence on the society and the policy making. So which we can say that it is bottom-up mode. On the contrary, online news are published in terms of policies or crucial events, where information goes through top-down direction. This is also the reason why keywords extracted from Twitter are more up-to-date than what we get from news. In order to understand the relationships among keywords, we build up the network of keywords based on their co-occurrences. So the thicker the edges are, that means the more co-occurrences these two keywords have. So for the Twitter network, we can separate them to the photovoltaics, smart grid, and smart home. And for online news, we can separate them here, like this. Left part is smart appliances, right part is self-electricity. So the networks somehow still looks a little bit messy. That is a reason why we bring interactive symbol chart into. It is easier to check the keyword relationships. Like here, you can click the smart home and zoom in. And you can see the detail of different keywords and just click back to another keywords, topics, keywords. Okay. Now we come back to the presentation again. In general, topic distributions of Twitter and online news are quite similar. Both of them lay emphasis on energy production and smart home, especially energy production takes the largest share. Although Twitter focuses on photovoltaics here and online news has a broader horizon, but they are still quite similar. The only difference is that Twitter has a clear small topic called smart grid, while online news merge them into a smart home direction. Although topic descriptions of Twitter and online news are quite similar, their temporal developments in Germany are quite different. The number of tweets has two clear peaks. The first one is in the March 2012, and second one is around November 2017. In order to find the reason why it developed as this, we decompose this trend into different components in terms of topics. So the topics of photovoltaics lead to the first peak. Renewable energy policy in 2009 largely boosted the installation of photovoltaic systems in households, and in 2012 they tried to slow it down, which perfectly explains why the amount of tweets starts increasing from 2009 here and directly go to the first peak in 2012. Policy, especially for the financial support policy, can have a strong and real-time influence on the discussion. So now we see the second peak. It is caused by the smart home topic. Between 2016 and 2017, Amazon, Apple, Google, Philips, and other technical anchors released their new smart home products. which contribute to the soaring to it. However, commercial events had a long propagation period, so that they have a slow impact on the social diffusion. Now we go to geographical diffusion analysis. Before 2010, photovoltaics dominated the smart building concept. Therefore, Baden-Württemberg and Bavaria will have more solar resources and the better industrial foundation lead the concept diffusion. As the booming of photovoltaics boosted by the policy from 2009, the differences among the whole Germany is reducing. With the growing percentage of smart home topics, North Westfalen even starts to lead the diffusion from 2014, since it has a centralized digital policy which strengthens their usage of digitalization. In conclusion, relative natural resources and the industrial foundation play a vital role in the early stage of smart building concept diffusion. However, both national and regional policies has more impact on its diffusion process. As the concept matures, differences among regions will become less. In total, we have over 84,000 users within the smart building concept, but most of them only sent 1 or 2 tweets about smart buildings. An interesting finding here is that 4 of 5 top accounts with the highest retweets of their posts are private users, which means end users themselves play a prominent role in the user engagement. This situation also reflects that neither big companies nor policymakers specifically work on this concept to nudge its diffusion toward end users, but only for the startups works here. Based on the result of our analysis, we derived 4 policy recommendations. So first, focus more on consumer business models. So what is consumer? That is consumer plus manager. So the end user is not only consume energy, but also produce energy and manage their energy, or we say storage the energy. The policy-oriented online news focus on the abstract concept of energy efficiency. They widely ignore the biggest advantage of smart building is flexibility. But this part is most popular topic discussed on Twitter, which means end users really care about that. For the end users, financial aspects are always very relevant. When policymakers or energy companies highlight the advantage of combining photovoltaics and electricity vehicle charging or intelligent energy management systems or even energy storage, and provide the corresponding business models, more and more end users would be attracted by smart building services. So policymakers can tackle these opportunities by more strongly supporting the development of major business models and by emphasizing the advantages of major business models towards the public. Then the second recommendation is about speed up the provision of digital infrastructure. Actually, apart from providing crucial digital infrastructures, policy measures should also boost the training for digital tools, in particular for the relative participations, like installers, sellers, managers, and so on. So before these new technologies come to end users, this participants should be trained how these things works and how they can sell them. Otherwise, the end users cannot know who can support them to use these new technologies. The third recommendation is about startups. There are plenty of startups in both photovoltaics and smart home domain. However, they do not have a significant influence on user engagement. and they even need support to broaden their market. Apart from direct give the financial support, building up connections among startups, even with established enterprises, can also strengthen their power to attract end users. The last policy is around policy recommendation is around social media. Although online news can interpret policies or crucial events, there is still a delay and a content gap between the publishers and the end users. Twitter and other social media can break up this bottleneck. However, until now, only startups have made full use of social media platforms in the context of smart buildings. Governmental entities could also set up official social media accounts to provide accessible and neutral information on the smart buildings, so that end users can get access to reliable information and get more willing to adopt this concept. Apart from content contributions I just introduced, this paper also brings two data perspective contribution and four methodology contributions. Now I'm very grateful for your comments and any question about our project.
I think it was a very interesting presentation, and it really shows how we can use social media and Twitter. But due to the time, I think I will leave it to Horia to finalize this session.
Yes, I think we still have time for one question, if you have one. I think we have 3 minutes left for that.
And if there are no questions, then I have one, and it is if you could elaborate a little bit more on how we can use your research in other areas. As I understand it, you're very much focused on the renewable. Let's imagine that we talk about energy efficiency, and that we would like to nudge homeowners also to work with the energy efficiency. Do you have any ideas about how we could use your setup for that?
So actually, we are creating a really generative tool. So it's just so all this kind of methodology, not only for use for the renewable energy or only for smart buildings. So if you search more keywords, like for example, your start, or we say the root keywords is energy efficiency, then what you got is for the energy efficiency topics. So it's more like depending on which kind of input keyword, basic keyword list you have, and then the whole workflow or the whole pipeline you can use for different kind of domain. So it's more than, so we want to bring this methodology to the whole domain. So it's not really limited.
Great.
I think a lot of companies could be interested in working with that tool.
Yeah, I would think of it's quite easier or quite good way to really know what the users really want to really think. So at least, so for example, so we can get like millions of user data rather than only we send off surveys for small data set, and the visualization is more easy for us to really understand, although maybe you are not for the informatics or data scientists, but you from the visualization from this tool, you can really find the trend or what you want to find. Yeah.
Thanks.
And we have a short question to Jiao from Katarina. How did you limit the search only to Germany?
So from the Twitter, they have a geography tag. So you can just limit the tag to Germany. And for newspapers, and they have the publisher information. So you can just limit the publisher information to Germany.
Okay, Thank you. And thank you very much for all speakers and for the discussions and the presentations. We come to an end. I just want to have a small announcement that there is an extra session at 2:15 p.m. just to wrap up the conference with the reflections from the whole week. And you can find the details on Huva agenda. So thank you again very much for this smart and very interesting session. And hope to see you soon. Thank you very much.
Okay. Thank you.
Thank you all.